Okay, welcome back to this session on spread spectrum communication systems. So as I said in the previous class, I discussed about what are the characteristics of a spread spectrum signal and what is the model of a spread spectrum communication system, right? So I said the spread spectrum communication model has a channel encoder and channel decoder, then modulator and demodulator. In addition to these four blocks, it has pseudo noise code generator, it is the modulator and demodulator. So that is the difference between conventional communication system and the spread spectrum communication system. Sorry. So having this pseudo noise code generator in the modulator and as well as the demodulator, so it is possible to achieve the secure communication, right? So that is why I said it started developed in the military, okay, for having secure communication. So just to share the full screen. Okay, I hope all have come. Only 24 students have joined. Having that most the key control. Pressed out. Okay, what happened? There any this one? No. No. Okay. Awareness. Okay. Yeah. Fine. So just to have an update, what I said. I said the pseudo noise code sequence is used at the transmitter to spread the information bearing signal into a wideband signal. Okay, so that will be transmitted over the channel. So the purpose is to have security. Right? You can think that take a piece of bread and take a jam also. Okay, spread that jam over the entire piece of a bread. I can correlate like that. So jam is your information bearing signal and bread is the channel bandwidth. So we are spreading the jam over the entire piece of a bread, right? Then transmit over the channel. So by doing like that, okay, at the receiver, so what we do is we multiply that received signal with the same pseudo noise code sequence, okay, to despread the desired signal. Means at the transmitter side, we are converting this information bearing signal, which is of low frequency signal or narrowband signal, into a wideband signal. At the receiver, we do the reverse process. So we do by multiplying with the same pseudo noise sequence, we'll be able to get back the despread signal, right? Means we are converting that into a narrowband signal, right? So along with the interference, so that interference will be still have a wide bandwidth. Okay, so the net effect is we are going to reduce the interference power by a factor of W by R, where W is the bandwidth of the channel, I can say, and R is the bandwidth of the information signal. So W by R. So, and this is also known as the processing gain of the spread spectrum system. Okay, so I said that the pseudo noise sequence is assumed to be known only to the intended receiver. Okay, and At the receiver, the people who do not have this code, they will not be able to get the desired information signal. Okay, so the use of the pseudonymous code sequence provides a high degree of security, and which is not possible in the conventional communication system. So what is the cost we are paying for this is means to have security and sorry, as well as there is an improvement in the performance gain against interference is the increase in the channel bandwidth utilization. Okay, that is the cost we are supposed to pay. Increase in the channel bandwidth utilization, and as well as the complexity of the system is also increases. Okay. Complexity of the system also increases. So these are the costs which we are supposed to pay for having security and improving the performance of the spectrum system. So this is what I discussed in the previous class. So now let me discuss what is the effect of.
Sir, your voice is
Yes,
not audible properly.
not audible.
Communication.
Sir, there are people trying to get in, sir. They're not able to get in.
Sir, your mic is off.
Sir, can you hear us? We can't hear you. I think he's also not hearing you.
Sir, you're on mute.
Do like this, no.
Okay. Fine. Is it audible? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
So some cannot access this, so you need to let them in.
Why?
So they're trying to get in, but they're saying they can't.
I enabled waiting room, but already people I keep admitting now when they're joining. Almost 35
Okay.
35 people have come. Now no one is in waiting room. Okay. So,
Okay.
yeah. As I said, I think this screen is okay, no? This much. It is clear, no? The screen.
Yes, sir.
Yes, sir.
Yeah. Already I discussed about this block diagram. As I said, the received signal will be multiplied with the pseudo-noise code. The purpose is to display the signal. Then it will be passed through the correlator. The purpose of correlator is again to get the demodulation signal, right? Then output of that will be sampled and we'll be getting the decoded signal. Okay, now our aim is to find out what is the effect of interfering signal on the despreading of the, while despreading and getting the desired information bearing signal. Okay, so to understand that, let me write mathematically the received signal R of t as what? AC V of t C of t cos 2 pi fct plus I of t, right? So AC cos 2 pi fct is the carrier signal. That is after modulation I get that. V of t is my information signal. C of t is a pseudo-noise code. Right? Along with that, the interference signal will be there. Plus I of t. Means interference signal is added to that. Right? So while despreading, what do? First, I multiply the received signal by the pseudo-noise code. So R of t into C of t. So which is equal to what? AC V of t C square of t cos of 2 pi fct plus I of t into C of t. And as I said, c square of t will be equal to 1. Hence, that c square of t will be replaced here. Right? So I get AC V of t cos 2 pi of ct plus I of t into c of t. So here, what we are doing is the interfering signal or interference signal is also multiplied with the pseudo noise code. Okay, means that is also spread over the entire bandwidth of the channel. So the effect of multiplying the interference signal with the pseudo noise code is to spread the bandwidth of that interference signal to channel bandwidth. Okay, so let me consider the sinusoidal interfering signal as an example. So I denote that as I of t, which is equal to AI cos 2 pi FIT, I write. So where Fi is the frequency within the bandwidth of the transmitted signal. So the multiplication of the interference signal with the pseudo noise code results in a wideband interference signal, right? The power spectral density of that interference is, see, Reddy is joining now. You wanted to admit now. So I naught is the what power spectral density of the interference signal, which is equal to Pi divided by W, I can write. So where Pi is the average power of the interference. Okay, average power of the interference. So Pi is equal to, I can write AI square by 2. So average power will be, AI is the magnitude of the interference signal. So square of that divided by 2 is the average power of the interference signal. So the desired signal is demodulated, as I said, either by using master filter or by using correlator. Right? That has the bandwidth of RHz. So the total power in the interference at the output of the demodulator, at the output of the demodulator can be written as, so I naught into RB. See, I naught is the power spectral density of the interference signal. RB is the bit rate of the information signal, right? So I naught into RB, so which is equal to, just I am substituting I naught as Pi by W. As I said, I naught is the power spectral density of the interference signal, right? So I am substituting in place of I naught as Pi by W. So I can write this Pi into RB divided by W, right? So this can be rewritten as like this, Pi divided by W by RB. So whatever is there in numerator will be, I can write like this, right? It's just for my convenience, I'm writing in this way. Then, which is equal to Pi divided by, see, W by RB. As I said, 1 by RB is TB, right? TB is the bit duration. And TC is 1 by W. So I can write this W by RB as TB by TC. So this TB by TC is nothing but the processing gain of the spread spectrum system. So that is why I'm writing this is equal to Pi by LC. L suffix C is the processing gain of the spread spectrum system, which is equal to TB by TC. Okay, so please have a note of this equation. Okay, this is the total power in the interference at the output of the demodulator. So the power in the interfering signal is reduced by an amount which is equal to the bandwidth expansion factor of the bandwidth expansion factor. I said the bandwidth expansion factor, which is equal to what? W by R, right? W is equal to 1 by TC, R equal to 1 by TB, I can write. So so that one only is written here. See, W by R, so which is equal to, as I said, R is 1 by TB and W is 1 by TC. So I can write it as TB by TC. So TB by TC is nothing but LC, which is known as the processing gain of the spread spectrum system. So if I know what is the bit duration and what is the chip interval duration, I will be able to say what is the processing gain of the spread spectrum system. Okay. So the reduction in interference power, okay, is the basic reason for using the spread spectrum signals to transmit digital information over channels with interference. Okay, so why we use spread spectrum signals okay, to transmit the digital information over the channels with which is having interferences, because there is a reduction in the interference power. That reduction in the interference power is how much? It is W by R. So I think, yeah. So please have a note of this example. Okay. So the signal to noise ratio required at the detector to achieve reliable communication in a direct sequence spread spectrum communication system is 13 dB. So this is the amount of SNR we require. Okay. So if the interference to signal power at the receiver is 20 dB, then what is the value of processing gain I need to achieve the reliable communication? And okay, so here for this direct sequence spread spectrum communication system, the average probability of symbol error, since I'm using BPSK as a modulation technique, so that will be equal to Q of root of 2 EB by I naught, I say, where I naught is the interference signal. Okay, there I used to say 2 EB by N naught, right? N naught by 2 is the spectral density, power spectral density of the noise. In the same way here I'm saying it is I naught by 2. Okay, so here he has given the required signal to noise ratio, means it require 13 dB, right? And he has given what is the interference to signal power at the receiver, which is 20 dB. So we need to calculate what is the processing gain required to achieve reliable communication. So I have written here Pi by Ps. Pi is the interference power, Ps is the signal power. Okay, so that will be equal to what is given 20 dB. So in terms of ratio, I can write it as 100. And he has given SNR, signal to noise ratio. Okay, to the detector is 13 dB. So in terms of ratio, I can write it as 20 it is. Okay, and this is the formula for signal to noise ratio at the detector. So which is equal to 2 times PS into TB divided by PI into TC. Okay, this equation we have taken from the previous this one. So you need to remember this, because I'm not going to derive this equation how I am getting the SNR as this. So 2 times the signal power into the bit duration divided by the interference power into the chip duration. Okay. And see again, I'm doing some rearrangement. The TB by TC is nothing but LC I said, right? So I can write that as 2 PS, 2 times the signal power divided by interference power divided by LC. So LC is the processing gain. So I wanted to calculate SNR, right? So to calculate SNR, to calculate this one processing gain, I need to rewrite this equation in terms of LC. The LC is the processing gain. So I'm doing that. So LC is equal to, I get this 1 by 2 into Pi by PS into SNR at the detector. So I know what is the value of Pi by PS and I know what is the value of SNR. If I substitute those two values, I will be able to find out what is the processing gain, right? So 1 by 2 into Pi by PS is 100 and SNR is 20, and which is divided by 2, right? So 50, yeah, 100 into 20, I get it is 2000 by 2 is 1000, right? So I can say the processing gain required is 1000. To say in terms of dB, it will be equal to 30 dB. Okay, this is one example which we can understand. Means they give what is the required SNR, what is the interference to signal power ratio to the receiver, and they may ask you to find out the processing gain. You need to use these formulas. Okay, so next one is interference margin. Okay, the interference margin, we will be able to express this as like this. See, EB by I naught. EB is the bit energy, okay, and I naught is the power spectral density of the interference signal. So which is equal to, so EB can be written as PS into TB, means signal power into bit duration. So I naught can be written as what? PI by W. Just I'm substituting from the previous equation, right? So TB is 1 by R. right? So I'm writing that as PS by R and PI by W. So with this is equal to, I can write it as W by R divided by PI by PS. Okay. So I can use log for this. Means if I want to express this interference power to the signal power in terms of logarithm, so I can take 10 log of PI by PS, which is equal to so 10 log of W by R minus 10 log of E by EV by N naught. Right? So this in terms of dB is equal to 10 log of something can be PA by PS in dB, which is equal to so W by R in dB minus EV by I naught in dB. Okay, means EV by I naught is equal to W by R divided by PI by PS. So PI by PS is equal to what I get, and W by R divided by EV by I naught. So that is, if I take log, you all know it is log A by BS, log A minus log B. So just I use that formula and I'm writing here. So this ratio PI by PS is known as the interference margin. Okay, so interference power to the signal power. So based on this equation, I have taken one example. So let me take down this example. Suppose we require an EV by N naught, okay, which is equal to 10 dB to achieve reliable communication. Okay, to achieve reliable communication. So what is the processing gain that is necessary to provide an interference margin of 20 dB? Why people are signing out and joining? So here the value of EV by N naught is given as 10 dB. Okay, and he says means this is the required value of EV by N naught to achieve reliable communication. And he's asking us to calculate what is the processing gain that is necessary to provide an interference margin of 20 dB. So just now in the previous slide, I have shown what is the relationship between signal power, means interference power to signal power, right? So PA by PS is W by R minus EB by I naught. So the EB by I naught is given as 10 dB. So I need to calculate what is the signal to, means interference signal power. That is what the interference margin is, right? Means if I take a W by R as 30 dB, right? From that equation, 30 minus 20, see 30 minus EB by naught is 10 dB. Okay. So this is not correct. Signing out, signing in. See, every time, why people can sign out?
Because of network issues, sir.
Network issues. Okay, that is fine. Okay, I think you could get now this EB by N naught is given as 10 dB and he has given interference margin as 20 dB. I need to calculate what is the processing gain required, right? So if I take W by R as 1000, in terms of dB, it becomes 30 dB. Then already has given, means PA by PS as 20 dB, right? And he has given EB by N naught as 10 dB. So I can calculate what is the value of this one. I think from this, see, he has given PA by PS as 20 dB and EB by N naught, EB by I naught as 10 dB. So I can calculate what is the value of W by R, right? So this is 20 and this is 10. So 20 plus 10 is 30. So W by R will become 30 dB. That is what is done here. So 30 dB is nothing but, in terms of ratio, it will be 1000. So W by R. So what is the meaning of this is, though the average interference power at the receiver may be 100 times the power of the desired signal, still we will be able to have a reliable communication. That is what the meaning of this is. Okay, then the last topic in this one is performance of coded spread spectrum signal. As I said, the first thing is we pass the signal. When I discussed about the model of spread spectrum model, so during that time I said channel modeling, right? Channel coding. So here, when the transmitted information is coded by binary linear code, so that may be block or convolutional code, the SNR at the output of the decoder, okay, large SNR uh, is increased by the coding gain, so, and which is defined as like this. So coding gain will be equal to RC into D minimum H. So RC is the code gain and D minimum H is the minimum Hamming distance of the code. I think you are aware of what is Hamming distance and all. So this is the expression for coding gain. Okay. So the effect of coding is to increase the interference margin by the coding gain. Okay. So I can write Pi by Ps, which is equal to W by R plus coding gain and minus EV by I. Okay. So CG is the coding gain in dB. So by having coding gain, I will be able to increase the interference margin. That is what the net effect is. Okay. So what is this? So if you have any questions, you can ask me about this. Here, some of the relations I have taken because SNR and all. So straight away I have written. You need to understand that, but the rest of the things I feel it is okay. Two problems I have taken. So if you have any questions, you can ask me. So as I said, with the use of coding, okay, it is possible to increase the interference margin. Yeah, let me take the attendance.